All right, folks, I see that we have close to 30 people joining us, which is about normal. And it's a couple minutes past the hour. So I'll just remind everyone, we're all accustomed to Zoom meetings now. We're all muted and our videos are off, so that's great. During the presentation, Tim, do you have a preference for people to interrupt you and ask questions or to hold them until later?
Totally up to you. Doesn't matter to me.
Okay.
If there's something that's totally not clear, I would say interrupt.
Absolutely. Okay. So if you do have questions that you don't want to interrupt Tim with, but you think of along the way, feel free to type them into the group chat and I'll moderate the discussion at the end and make sure your question gets addressed. So it's a great pleasure for me to introduce Tim Barfoot today. Tim is a professor at the University of Toronto's Institute for Aerospace Studies, where he works in autonomy for mobile robots. He's chair of the U of T Engineering Science Robotics Option, associate director of U of T Robotics Institute, and a faculty affiliate of the Vector Institute. Tim obtained a Bachelor of Science from U of T's, I'd say, notoriously challenging engineering science program, and a PhD from U of T's Institute for Aerospace Studies in Robotics. He's worked at MDA Robotics, who are the folks who build the Canadarm space manipulator, where he worked on autonomous navigation for planetary rovers, as well as terrestrial applications such as underground mining. Tim was a visiting professor at Oxford. He was director of autonomous systems at Apple for a few years, and he sits on several editorial boards, including IJRR and JFR. And he authored a book, State Estimation for Robotics, which is freely available on your webpage. Is that right, Tim?
That is right.
Very good. So everyone go download that and read that tonight, and we'll have some questions on it for you tomorrow. Tim's research involves developing new methods in localization, mapping, planning, and control to enable long-term and large-scale autonomy in unstructured, three-dimensional environments using rich onboard sensing and computation. And today he's going to talk to us about reliable and generalizable robot navigation with lots of videos of robots. So without further ado, please do take it away, Tim.
Okay, great. Thank you so much for the invitation. And I'm excited to be in Australia. I haven't actually been to Sydney, so this is the closest I've come so far. But hopefully I'll get to visit you in person at some point before my career is over. Okay, so I'll jump right in. I won't talk about this video that's been on the first slide, but we do actually have an undergraduate self-driving car team. So this is all built by undergrads, and it's quite a fun project. So today I broke the talk into two parts. I'm going to spend some time talking about some past projects where we've been trying to build up reliable robot navigation solutions that can operate in the real world. I'll talk about this ongoing affair we have with a framework that we call visual teach and repeat. And I'll do a bit more of a deep dive on one aspect of what we've been dealing with in the last few years, which is dealing with appearance change. So if you're navigating with cameras. And in the second part of the talk, I will give you a bit more about what's going on at the bleeding edge of our lab in terms of some current projects. And this is where I'll start to talk about this push towards generalizable autonomy and the idea of a template for a navigation solution. And in particular, how can we build templates without expensive ground truth labeling for a lot of the data that we need to build up robot navigation solutions. Okay, so let's go into the first part of the talk. And I'll just give you one slide on kind of what I'm interested in. Thought I'll give you a nice overview of kind of my interests. I've worked in state estimation, which I think of as perception mapping, localization tracking, as well as planning and control. And kind of the size of these circles, I guess, is figurative for how much time I've spent on these different topics. A few highlights from the lab over the years. In planning, if you're a planning person, you may have heard of the informed RRT star or the bit star algorithms, which sort of take RRT star and try to make them more efficient, in particular efficient enough to work in high dimensions, so freely downloadable code for those. We've also worked on some SLAM type problems. In particular, we extended SLAM to a framework that we call STEAM, which goes from discrete robot poses to continuous functions of time for robot trajectories. And these tools can be quite useful in problems where you've got a sweeping while moving sensor. So for example, a lidar or a radar or a rolling shutter camera, where you can't really say that every datum from one of these sensors comes from the same robot pose. We've done some work on control, in particular, combining learning with control. So we're seeing an example here of a robot that's trying to track a path, and it's trying to build a better model of itself by looking at its own path tracking errors as it repeats the same path over and over. And the idea is as it gets a better model of itself, it can actually try to drive the path faster and faster and more accurately. And then what we'll mostly talk about today is one of the frameworks we've worked on to try to integrate all of these different component modules into an overall navigation solution, in particular this one that we call Visual Teach and Repeat. So I won't describe it because I've got a whole next slide that's going to talk about that, but I kind of think of that as it's not just a useful tool in and of itself for robot autonomy, but it's also kind of like a good petri dish for exploring different component algorithms, because we can plug them into this framework and see how they fare as part of a larger autonomy system. Okay, so what is this Visual Teach and Repeat that I've mentioned a few times? So as I said, it's a full robot navigation framework that basically allows a robot to navigate, in this case, using only vision in any environment. So we don't assume any particular structure, like a self-driving car in terms of roads with traffic signs and lanes and these kinds of things. VT&R works with one laptop, one camera, a stereo camera, one training example of each path. So we actually get a human to drive the robot along each path that it's going to be repeating once as a training example. We don't use any GPS, we don't use IMUs, no DNNs, no global map, and no semantics. So it's very bare bones. And the general idea is that, as I said, a user will take a robot and drive it along a path, which we will build a map from a rich sensor, such as a camera, along this path. And we'll use this to then allow the robot to localize itself against that path to drive the path autonomously. And so you can see an example on the left side of the slide. I think you can see my mouse if I move it around. All of these yellow paths were demonstrated to the robot. In fact, this is an interconnected network of paths, 5 kilometers of paths that were taught to the robot. So one training example of each segment. And then the idea would be to quickly show the robot all the places that it's able to drive and then have it autonomously drive on that network of paths essentially forever. That's sort of the overall goal. And you can imagine there are a lot of challenges around that. If you want to try to do it using vision, we can see even in the picture some examples of quite different lighting conditions that the robot might encounter. And it's only had the one training example of each path. So that's kind of what we've been working on for about 10 years. Here are some older examples of VT&R in its infancy, I would say. On the top left, we've got a robot driving in a really barren environment using stereo up in the Arctic. In the middle, we've got some code that was deployed to a $11 million rover prototype at the Canadian Space Agency. Again, on the top right, another rover at the Canadian Space Agency that happened to be driving as Hurricane Sandy blew through. So it was sort of emulating a dust storm on Mars and changing the environment visually. And we were able to continue to drive. And then in the bottom, we've got something a little bit more than teach and repeat. Here we've got a robot that's actually trying to teach itself a path from a start to a goal. And the idea is it's kind of like an embodiment of a tree search. So the robot is branching off this tree that it's building up, and every time it finds a dead end, it uses our visual teach and repeat algorithm to backtrack along the tree towards the root and then branches off at a different place. And eventually it can discover a path from the start to the goal without knowing a map of this terrain in advance. And once it's established that, it can actually just autonomously drive back and forth between that start and that goal as many times as it likes. So there are some applications in planetary exploration that could make use of that. We've also deployed a visual teach and repeat algorithm actually even before all these vision videos that I just showed you, where we're using a lidar for an underground mine truck. I know a lot of the early underground mining started at U Sydney, so this is my shout out to all of that work that we built on. This is a 14-ton scoop tram driving in a mine autonomously. There's nobody in the cab, and it's using this visual teach and repeat to navigate up and down the hallways. So again, an operator would show the robot the paths that it's allowed to drive, and then it can operate on those autonomously. More recently, we've been deploying this framework onto unmanned aerial vehicles. We're collaborating with a company that does delivery in the far north of Canada to remote Inuit communities. And the idea is that we would like a fallback if GPS were to fail. So the idea is we're flying under GPS control, and eventually we might experience something like a GPS failure, but because we've built up a visual map on our outbound pass, we can then use that to localize and backtrack towards the start without using GPS. And so here you're starting to see some of the inner workings of the algorithm. some features that we're tracking, and we're using those to build maps. And then one last example of where we've used some of the underlying localization technology of teach and repeat. We've actually been working with the local transit commission to see if we can improve on the positioning of transit trains in the Toronto transit network. So it turns out, I didn't know this, but most trains are actually positioned using RFID tags, which means the precision of the localization of the train is like between 10 and 100 meters, which is not particularly good. And it turns out if you could actually have much more precise localization, you could pack more trains onto the same tracks because you can know where they are more precisely. In fact, it turns out if you could know where you are very precisely to a few meters or 10 centimeters, you could put twice as many trains on the Toronto TTC tracks and thereby double the capacity without changing the tracks. So this is actually showing that we can localize using similar infrastructure that we would use in teach and repeat down to sort of a handful of centimeters using just a planar SICK laser rangefinder. So we've been working on this framework, visual teach and repeat, for, as I said, about 10 years. Deployed it on lots of different robots, had partners deploy our code on different robots, everything from these unmanned aerial vehicles to the sort of tank-like vehicle that you see in the bottom left of the screen. Learned a lot about different things. And in particular, now we've gotten to the point where we've sort of robustified the code enough that in the bottom right, you can actually buy a license of our teach and repeat software from ClearPath Robotics. So they'll deliver you a robot with our visual teach and repeat software on it.
Just
Hey, Tim.
quick question from Viorella, Ela. So she's asking whether the existence of a path that is wheel tracks is a requirement for this to work.
Like, do we need to be able to see the tracks? We do not need to be able to see the tracks. We just need to be able to have a textured environment where we can have some interesting landmarks to track.
Okay.
Yeah, I also just wanted to ask, with this sort of single shot demonstration, are you then updating the model as in subsequent repeats so that, you're kind of learning how this is changing through time? I think I've seen you show this in sort of summer, winter. Presumably there's some learning that sort of sits on top of all that.
It's coming up. You're anticipating the talk.
Sorry.
It's coming up. I'll get to it. Very soon I'll get to it, actually. Okay, I'll keep going. So as I said, visual teach and repeat is a tool in and of itself, but it's also a bit of a petri dish for letting us try out different things. We've played with everything from learning to improve path tracking. I showed a video for that. Learning to assess terrain. Route planning through a network of paths under uncertainty. And in particular, the thing that Steph was just talking about is how can we start to handle appearance change? So obviously anyone who's used vision outside realizes that if you just do a single shot demonstration where you're building a visual map, that can start to break pretty quickly when the lighting conditions or something else even longer term starts to change in the scene. And so I'm going to do a bit of a deep dive on that, how we start to handle appearance change in the system. Okay, so before I get to that, I need to talk a little bit about the map structure that we use in visual teach and repeat. So it's actually a very lightweight algorithm in some sense. So the very first thing we do when we're demonstrating the path, which is what this blue path is meant to represent, is that as the robot's driving along, we're running visual odometry. So we're tracking some landmarks, usually surf features, 3D triangulated surf features in the environment, and we're estimating our motion. And then the thing that we do on top of VO is that we actually store the landmarks that we're using to estimate our motion, and we store them, very importantly, relative to the first pose at which they were seen. So we don't store them in a global frame. And what this basically means is that we have a fully relative map structure. So we've saved all the transforms between these robot poses, these triangles, and we've saved all the landmarks relative to those triangles. So that's the teach pass. In the repeat pass, we come along and we now want to localize a new robot pose, this red triangle, with respect to that path so that we can make sure that we track it. And so we can identify some similar landmarks, but the important thing is we can actually just draw a red rubber band kind of around the local region that the robot's in. And it's very easy to sort of remove the rest of the map because everything is defined locally. So we only really need to consider everything that's going on inside this local red rubber band. So if we can identify some common landmarks that are stored in the map, we can then work out the transform from the red pose to one of the poses on the path, which is what we need to then send an error to our path tracking controller. Then the robot moves forward. We actually also run VO in the live sequence of images, so we can estimate this transform. And in this case, I'm showing an example where the robot does not observe any landmarks that are stored in the map. And so it doesn't get to correct itself, but it's already had a good prediction from VO. And so it can go for a while just on VO. Then we go forward a little bit more. We can identify some landmarks in the map again, and then we can get a correction to figure out what this transform is from the red pose back to the path. And of course, if we know the transform back to the path, we can actually look ahead at the shape of the path and run something like model predictive control to work out the sequence of commands that we would need to zero the errors as we move forward. So that's pretty lightweight. I will note that we don't have to actually run SLAM in a global frame. Because everything is done in a relative frame, we make no attempt to actually make our map make sense in a global reference frame.
Another quick question for you, Tim.
Yeah.
Question here. So you're picking a neighborhood, and the question's from Iman Shames, who's asking, how do you know that you're picking the correct neighborhood?
Yeah, because we're not really solving the kidnapped robot problem. We're typically tracking, right? So we actually only need to, it's very easy to sort of know which pose is the closest one to the current robot pose simply by matching to a few in the neighborhood of our last successful match. And from that, we can kind of say which of these poses along the path is the closest one. But we don't need to know exactly because we actually localize against a window of these at every time. But we're never trying to solve the global kidnapped robot problem because we're tracking.
Yeah, thanks.
Okay, and so just to underscore the point that we don't have a global reference frame for our map. In fact, if we were to have a loop like I had in the earlier example, we had lots of interconnected paths. We actually make no attempt to make all the transforms add up to identity transform around one of these loops. And it's kind of like this Escher staircase, right? If you look at it locally, it all sort of metrically makes sense, but globally, it doesn't make sense. But that doesn't matter because in our problem, we're actually making all of our decisions locally. And we're only ever using one of these red rubber bands around some local region of the map. And that means we don't have to waste time relaxing everything into a global reference frame to make our map. So to start to deal with appearance change now that we know sort of how the map works, we tried a number of things in the past. So if we're always trying to localize the live image, this red triangle, back to the map, if we're only ever using this one map that was built under one particular lighting condition, for example, you're going to run into some problems as the light starts to change. And so we've tried a couple of things over the years that didn't work so well, I'm going to say. So the first thing you could try to do is change the sensor, right? So we did a bunch of work where instead of using cameras, we were using this fancy lidar that could produce intensity images way back like 10 years ago. And then we tried just tracking features in these intensity images instead of in regular images. And those images kind of look the same whether you're in sunlight or dark. And that worked okay, but it required like a $100,000 lidar sensor. So that isn't really something that's a good long-term solution. We also played around with this idea of color constancy and taking these transforms on the red, green, and blue channels that image in different wavelengths and combining them to sort of eliminate shadows. So you can see here some shadows in the image, the regular red, green, blue image, and then we've eliminated those in this color constant image that we can calculate. And it turns out that's actually pretty good. In daylight hours, that's a very cheap way of doing something that lets you continue to localize pretty much through all daylight hours, but not good enough to localize at night, for example. Even dirty tricks like putting cameras pointing in different directions so that you can sort of guarantee that not all of your cameras are pointing at the sun. So I would say these are all interesting things that we tried, and they're all kind of band-aids on the problem. And really, none of these allows us to sort of teach a path in the sunlight and then track it in the dark unless you use a very expensive sensor. So going back to just cameras, these are sort of all the conditions you might experience over 24 hours in one particular example. And you can kind of see like, there's really nothing, even I would say in deep learning today, that would allow us to match directly all of these lighting conditions. I mean, someone could probably correct me on that, but we've actually attempted to build deep learning matchers more recently, and even those start to struggle with sort of this condition against this condition. And so how can we actually get something that can still from the single training example of each path be able to localize as it experiences all these different conditions? The situation, of course, gets much worse when you start to talk about seasonal change. And so here are some traverses of the same path over about a 3 or 4 month period just outside of our lab. And you can see like everything from vegetation to a snowstorm at night with headlights turned on. And so trying to match those directly is going to be a pretty big challenge for, I think, any computer vision algorithm. I know you guys don't have snow, but this is what snow looks like.
Got to move to Australia, Tim. It'd be easier.
And so how do we do this? So we've gotten in, the solution that we sort of came up with for this long-term localization problem is the idea of not just actually matching against the single map that we built at the beginning, but as Steph was alluding, we can actually update the map over time. And so here's an example from the Canadian Space Agency's Mars emulation terrain, where it's about 7 hours different. And you can see these are the same place, roughly. The shadowing is quite different, and we're getting very few matches indicated by these green blobs in the image, just surf features between these. And as we start to drive around, we can see there's places where we actually get no matches. Sometimes we get matches, but quite often we're not getting any matches because the lighting has just changed too much. And so the solution is maybe we could actually not wait 7 hours to drive. Maybe we could have an intermediate experience that's sort of halfway between these two in time, which is the one that I've added at the bottom. And so now I can match the live image, not just against the original image, but also through this, what we're calling bridging image, which is halfway in time. And we can see now that the different colors in the top right are features that we're matching back to each of these two different previous experiences of driving the path. And if one bridging experience is good, surely 2 would be better. And if 2 is good, 4 would be even better. And if 4 is good, 1,000 and whatever would be even better than that. And so the idea is every time the robot drives the path, it's getting a new visual experience of what that path looks like, and we can add that into our database, and then we can use every previous experience of driving the path to try to localize the robot. At least that's the idea. What does that look like as we go back to the map structure? Well, now, instead of just having this one privileged original map that we had, where we had the human demonstration, which is the solid line, we now have all these intermediate autonomous traverses, and we can actually, instead of just red rubber banding one part of the original map, we can actually red rubber band sort of a spatiotemporal region in this spatiotemporal pose graph, and then we can try to localize this red vertex back against some vertex on the original path. And so we still want to calculate this transform between the live image and one of the vertices on the original path, because this is the path that defined the physical path that we want to, this is the experience that defined the physical path that we want to track. So we still want this transform, but we don't need to match these directly. We can match this to this, this to this, this to this, this to this, and that would still let us compute this transform. And so the secret to this is bookkeeping all of the uncertainties through the system, which is a bit of an exercise. But if we can do that, we can then actually continue to localize even as we're unable to directly visually match things from the live image back to the original demonstration. Of course, if you're listening carefully, you'll realize that how on earth does this scale, right? So how could we might be driving the same path thousands of times. Of course, we're gonna have to start pruning things off. And actually, even before pruning, we could just be selective in choosing which things we want to localize against. So this is a video from a 24-hour experiment where we had about 30 or 40 traverses of the same path. And we actually built a sort of recommender system that would take the live image, and it just used something like Visual Bag of Words to quickly compare the live image back to the previous experiences that we'd stored at all different times of the day. And these little green check marks are the recommended experience. And then we just metrically localize against those rather than all of the previous experiences. So we're kind of triaging and just selecting a subset of the previous experiences to localize against. And so that's sort of my summary of where we were like a couple of years ago. If you put all of that together, you have a system that looks like this video. So this is a 2-week experiment we did in Sudbury in northern, just about 4 hours north of where I live in Toronto. And so this was actually showed you the map of this experiment at the beginning of the talk on the first slide for visual teach and repeat. The robot is now autonomously traversing some of these paths. So we actually did about 200 kilometers of autonomous driving on this 5-kilometer network over a 2-week period. And you can see actually these ruts in the ground, those weren't there when we got there, right? Those are there because we've been repeating the same paths over and over so many times that it's literally etched itself into the earth. And you can kind of see the accuracy with which we're able to follow these paths. And I will say, like, the lighting and the weather changed significantly over that 2-week period. So we were doing experiments even in the dark with headlights. The Achilles heel, of course, is you can't let the appearance change too much before you redrive. Otherwise, there's going to be a gap in what the robot is able to match against. But this is one solution to being able to sort of span all the ways that the world can look, as my friend Paul Newman often says. And really, that's probably good enough for at least medium-term autonomy. Okay, so what have we been doing since this work? All the videos that I showed you up to this point were essentially working on surf features for the landmarks. And of course, the technology has moved on in these past 10 years. One of the things we tried before trying deep learning was something called GRIEF. So you may have heard of BRIEF features, which instead of surf, which is using a histogram or oriented gradients, BRIEF features use these little patches with these binary comparisons. So this white patch in the middle is sort of a blown up version of one of these patches, and these little black lines are the binary comparisons that it does in the patch. So the descriptor for this patch is essentially saying whether one end of this binary comparison is brighter than the other end. And so BRIEF sort of randomly picks these binary comparison lines within a patch. And then what we looked at was an algorithm called GRIEF. So GRIEF is actually a learning-based version of this algorithm. And the idea is you can kind of think of this collection of binary comparisons as like a population. And we run something like a genetic algorithm, a survival of the fittest algorithm to sort of evolve this pattern of binary comparisons over time. And we get labels for free because we're localizing as we drive along. And so we can kind of say like which binary comparisons are consistent with the matches that we're actually getting and which ones are not. Because, you know, after we run ransack, there are inlier matches and outlier matches. From the inlier matches, we can kind of say which of the binary comparisons agreed and which ones didn't, and then we can sort of evolve this population. And so the nutshell is that we can sort of learn a descriptor that's more effective for the path that we're actually driving live as we're driving. It turns out this actually works okay. Compared to surf, we ended up getting, in sort of the corner cases, about 2 times as many usable matches, but it's still a bit of a band-aid. It's not going to allow us to match daytime to nighttime, for example. But it was something that was useful, and it was pretty low cost to implement it. Another thing we've been looking at is getting away from features altogether and trying to use full image data. So this is an example from UAV navigation, where we were trying to directly match actually UAV images to rendered images from Google Earth. And this is a little bit of a similar problem to trying to match against, match across large appearance change that we saw on the ground vehicle. So in this case, we're actually using mutual information to try to align these images. That's been demonstrated in other contexts for even matching different sensing modalities. So we thought it would be a good thing for dealing with appearance change. And so we implemented, actually this is not running live on the UAV, but we implemented on data sets a new algorithm for localizing against these Google Earth rendered images. So in this case, we don't even have to actually fly the flight path in order to get the teach pass. We can just do it virtually in Google Earth and then have the robot try to repeat that same path. And we kind of showed that we were able to robustly match across even quite different lighting conditions back to the same Google Earth rendered images, which is what's coming up in the video right now. So here's an example, same place at different times of the day. These are images from the UAV, and we can see the shadowing is quite different, which presents quite a bit of a challenge. And so now we're localizing all those different lighting conditions back to the same Google Earth imagery and trying to show that we can match ground truth, which we gathered with a GPS INS system. You can kind of see just qualitatively that across all these different lighting conditions, our localization remains pretty robust. So by the way, on those same lighting conditions, surf features basically broke right away. And so this was already a bit of an advance for us. We haven't quite got that back onto the ground vehicle yet, but it is helping us. We're in progress of getting that working on UAVs. And then another thing we've been trying, of course, I haven't talked about deep learning at all, but we've been looking at, could we build just a better matching function using deep learning? And so here again, teach and repeat actually comes to the rescue for us, because what we'd like to do is sort of take these wildly different lighting conditions or visual experiences and directly match these to output the relative pose between these 2 locations. That's pretty challenging to do. Of course, you need a bunch of training data. And if you're going to do it as a supervised learning problem, you need training data with ground truth labels for the pose. And so teach and repeat actually lets us do this as well. Because we already have this multi-experience localization, we can actually take the transforms that we got while using bridging experiences as ground truth labels to match these things. And then we can try to build this deep neural network that doesn't require the bridging experiences in order to produce the pose. So we kind of think of this as like compiling the multi-experience localization into a DNN. And I'll just show you some examples of that. So we trained it both. We trained two different networks to do VO and to do localization. And we're kind of seeing here the results for VO, which is sort of like not even state of the art, but good enough for teach and repeat. And now there's going to be a video that shows sort of the results of trying to localize directly with this deep neural network. So this is at test time. We've got the teach image in the middle column and the repeat image on the left column. So matching snow to grass or green grass to brown grass. And on the right, we're sort of seeing an alpha blend of those two at the estimated pose coming into the network. And we can kind of see when these images line up well through the two images that are being blended, it means our localization is working well. And when it looks kind of weird, it means our localization is a bit off. We're not quite in the ballpark of localization being good enough to actually run this live on the robot, but we're close enough that I think that the idea has promise. Probably we need some more training data. The challenge here is that while we're able to do this reasonably well on the same path that we localized on, we cannot take that network so far and then use it to localize on a totally different path. And so this is just a way of compiling all of the existing experiences into a network for that particular path that we're going to drive, but it doesn't yet generalize. Okay, how am I doing on time?
Really good, Tim. We've got another, well, it's 10:36, so you've got until the hour. So please do take your time and run through it. If we run over a few minutes, it's not the end of the world.
Sounds good. Okay, just wanted to do a time check. So that's sort of like a good summary of a bunch of stuff that we've done over the last 10 years and even just the last couple of years. And now I want to talk about some of our bleeding edge current projects. So what I'm really getting interested in these days is this idea of, all these systems that I've shown you are, many graduate students working on these for many months or sometimes years to get to the level of robustness that we really want to see. And that's a lot of effort. And so what I've been interested in lately is, could we start to build more of a generalizable solution where we could just build a template for something like a teach and repeat algorithm and then drive the robot around, get a bunch of input-output data, and then fill in the details of that template and see how that goes. So I'm going to talk a little bit about that now. And I guess my philosophical slide of the talk is that, this is my state of affairs for robotics, I would say. There's some trade-off between the difficulty of the task that we're trying to solve and the generality of the solution. And of course, we would all like to be here where this green circle is. And I think a lot of the time, we sort of, at least in field robotics, we sort of compromise and head more along this direction where, we want to solve the hard problem, but we often overfit to that particular task. And I guess, part of me wants to keep going in that direction and just build better, more robust systems. But now I'm a little bit torn because I also want to try to build something that's a little bit more general and doesn't just overfit to one particular problem. And so I guess this is my attempt at bifurcating. I guess some students are continuing to push along the horizontal direction and others are going for generality now. Okay, so really VT&R, we'd like it, something like this, to work for any rich sensor, camera, laser, radar, on any robot platform, in any scene, so lighting, weather, seasons, geometries, dynamic obstacles, which I haven't talked about at all today, with minimal programming effort, and I think this is the big motivator. So it takes a long time to build a robust autonomy system. For VT&R, we still only want a single training example of every path, so one-shot training. And we still want to use minimal onboard compute, although I'm okay with using a bigger computer for training, for example, and really without using a human expert to operate the robot. So how could we do this? So this leads to something that I've posed for my lab, which is called the Mr. Potato Head Challenge. And the idea is, there are lots of very cool, rich sensors out there today, new ones coming on the market. So I don't know if you've seen this one, but the very far left is this NavTech radar solution, which is like a 360-degree spinning radar, kind of like a Velodyne, but in the radar spectrum.
And actually came out of ACFR, that one.
Oh, did it?
Yeah.
I didn't know that. It's a startup in Oxford, though, right?
Yeah, Phil and Steve were here when they did the first
awesome.
prototypes.
Okay, so you guys probably know a lot more about this than I do. That's great. So we'd like to take any of these rich sensors, kind of attach them to any robot base, and then drive the robot around manually, get a bunch of training data, and then from a template, auto-generate a visual teach and repeat algorithm that would work for that sensor on that robot. We're nowhere near being able to do that today, and I'm not going to get there in this talk, but I'm going to start to tell you an approach that we've started to follow along these lines. Okay, so for me, I'm going to get a little bit more mathy now. So for me, a lot of the underlying algorithms that we use in an autonomy framework for at least tracking paths kind of start at this graphical model, right? And so X could be the pose or the state of the robot, and this middle row is the latent trajectory of the robot. We know that as we apply inputs, the robot will move around and different things will happen. And at every pose, we get some sensor outputs, these Ys. And so this graphical model, and we can kind of break this into like past and future. And this graphical model is sort of at the heart of our different estimation and control algorithms, whether we like it or not. And so the idea, I guess, is, maybe we can keep the structure of the graphical model and then try to do something like learn the motion and observation models in terms of some unknown parameters theta. So could we gather a data set, an input-output data set for the U's and the Y's, and then try to learn the models. And then once we have those models, then we could sort of assume we know some of these random variables, some of the inputs and some of the outputs, and it's just an inference problem then on this graphical model to try to infer what some of the other variables are. So in this example, I'm showing, I know the past inputs, I know the past outputs, so I can do state estimation. I maybe have some desired future outputs, and I want to infer the controls that would be needed to make the robot produce those. So these could be like the images that we want the robot to try to make its output look like, and that would cause it to track a path. And we would try to infer the controls to do that. Of course, to do that, classically, we need to know these models, and so how do we get those? And I'm proposing to get them from data. And so kind of the focus in the learning problem is building up this input-output model of the robot. So we want to come up with these unknown parameters theta, which could be the sensor calibrations, both internal and extrinsic, where the sensor is located on the robot, the noise properties, the measurement covariances. If we modeled some of the nonlinearities for the robot, like its motion model or its camera model, perhaps as a deep neural network, then there would be parameters associated with those network weights. And so the idea would be, let's drive around, get an input-output data set, and then do an offline system identification to essentially learn all of these unknown parameters. So all of them together. That's my big hope. And so it turns out we can probably do this with expectation maximization, at least in the situation where the latent trajectory of the robot is unknown. So we don't want to assume that we have some fancy ground truth system that can give us the state of the robot at all times during the training. So really, we'd like to do it just in situ with the inputs and the outputs of the robot. And then once we've learned this model, the idea would be that we can then do online inference, for example, control, like I mentioned on the last slide. So we'd hold the model fixed, we'd have some of the random variables and try to infer some of the others. So we've been working towards a framework where we can do this, a variational inference framework. So we want to essentially often minimize this likelihood of the data given the model parameters. And so we can do this using expectation maximization. And you can do this typical decomposition for variational inference into these two terms, one that's negative definite and the so-called evidence lower bound. In fact, for us, it's the negative evidence lower bound. And the idea then is this thing I have in the green box, this V, we can alternately minimize this using the EM algorithm. So to do state estimation or inference, we hold the model parameters fixed, the thetas, and we optimize for the distribution over the latent trajectory of the robot. And then in the minimization step, where we're learning the model, we hold the distribution of the latent trajectory fixed, and we try to learn the parameters of the model. And if we alternate between these, we can eventually converge at least to a local minimum for this variable v. So that's what we would do offline to do system identification. And then online, we can just hold the model fixed and infer any variables that we want from the other variables. So of course, to do this in a variational setting, we have to pick some approximation family for this Bayesian posterior. So we're trying to pick this Q, which is our variational approximation of the full Bayesian posterior P of x given y, and u and theta. And so for us, we take the usual approach and we kind of assume that Q is a Gaussian, but it's a Gaussian over the whole trajectory of the robot. So a joint Gaussian, not a mean field approximation, but a fully correlated Gaussian over the whole trajectory of the robot. And so back to our problem, it turns out this idea is not new. It's been around for over 20 years. So Zubin and Sam looked at this at NeurIPS in 1999 and proposed a very similar approach, although they made a number of approximations and had different inference tools and modeling tools. So this was pre-deep learning, of course. And so in our setup, of course, what we're trying to do is in the E step, hold the weights of the motion observation models fixed and carry out inference for the latent trajectory. So trying to figure out the whole robot trajectory. And then in the M step, holding the distribution over that robot trajectory fixed and trying to infer, for example, if we had neural networks modeling the motion and observation models, we would be trying to do stochastic gradient descent on the weights for those neural networks. So that's sort of the big idea. And so we started to try to implement this, and it turns out there really weren't even good tools. We don't really use a lot of variational inference in robotics, I would say, other than for deep learning tools. But for things like state estimation, it turns out there just really aren't that many tools out there. And it turns out the first step we had to do was sort of build our own new inference engine. So we put out this paper last year. Actually, I guess it came out this year, called Exactly Sparse Gaussian Variational Inference. And so I won't go through too much of it, but I'll just give you the highlights of what it's about. So what it does is it shows how to fit the best Gaussian, both the mean and the covariance, to the full Bayesian posterior for these robot trajectory problems in the sense of KL divergence. So it's trying to find the best Gaussian over an entire robot trajectory that minimizes the KL divergence to the full Bayesian posterior. And it turns out people have done this before, but they haven't really shown how to do it tractably for large problems. So for us, the trajectory could be quite long. And so the state is actually very big. And the problem is if we're trying to estimate the covariance, that becomes quadratically big in the number of parameters. And so we showed that this is actually tractable for real problems, even when the state size is large, and even when there are loops in the graphical model. And so that means that it can be applied to all kinds of different inference problems, including SLAM, bundle adjustment, calibration, et cetera. We also, as a byproduct, show that instead of using derivatives, we can use sigma points or even more generally Gaussian quadrature methods in place of derivatives. And therefore, we actually show that you can do it provides a principled approach to doing batch state estimation without using derivatives, which I believe is the first paper to show that in the batch case. And then the part that we really cared about at the beginning that motivated this was that it also, because we're in this variational inference setting, it now allows us through this expectation maximization framework to neatly fold in parameter estimation. So that within sort of one framework, we can do both system identification and then inference at runtime for some of the variables. If we're doing state estimation, they would be just the trajectory variables, or if it was a control problem, it would be the control variables. And so you can check out those papers, they're online. I'm feeling a little bit like I'm not going to go through this slide and just jump to some examples of where we're using this to do parameter learning. So I'm going to show two examples.
Maybe a quick question on that last one. What's up? It's from Iman Shames. Is there a particular reason to pick the KL distance and why not some other distance measure?
Yeah, so there's a whole bunch of these, many, so there's essentially an infinite number of divergences you could define between two distributions. KL, to my knowledge, is the only one that has the nice property that if the graphical model factors, meaning we have not every variable correlated to every other variable, we can very neatly account for, we can take account of that sparsity to make the inference efficient, even when we're learning both the mean and the covariance. And so this is the trick, actually. Because we use KL, we can exploit the sparsity in the graphical model to make the problem tractable.
Okay, makes sense.
In fact, that's what the paper is about. Okay, sorry. Okay, I'll give you a few examples. So in this case, we've got a car that's driving around. It's got a Velodyne 128 on the top. It's localizing against a large HD LiDAR map. And the parameters that we want to learn in this case, we're not doing the full problem yet. The parameters that we want to learn here are actually the noise parameters, effectively. So we want to learn the noise parameters associated with our motion model and our observation model. The details matter a little bit less. But there's a paper that I reference later if you do want the details. Another example is we want to drive around and we want to try to do lidar-only odometry. And we're going to, in one framework, try to learn a set of 3D LiDAR landmarks to pay attention to for the odometry problem. And so we're coupling a deep neural network at the front end to try to extract landmarks, and we're training that end-to-end, essentially, within the state estimation framework. And so in both of these examples, we don't have any ground truth for the robot. So we're just going to drive around, and then from the input-output data sets that we gather, we're going to try to learn these different sets of parameters in a system identification step, and then use those models to then do, in the left case, localization, and in the right case, odometry. So I just have one slide showing sort of the results of this first problem. So this one is the one where we're localizing against a LiDAR map with a known matching function, and then trying to learn the noise models for our motion and observation models. And we purposely made this problem really hard in that we injected a whole bunch of outliers into both the training data set and to the testing data set. And we showed that even without ground truth, even in the presence of lots of outliers, we were able to learn reasonable noise models and get quite accurate state estimates after we learned the models. And so the bottom line is this plot on the left that shows we actually got quite good localization against this map after learning the noise models. And so you can reference this paper at the bottom. I can provide the slides after if you want to get into the details of that. I think the more impressive example is the second one, where we're trying to learn some 3D landmarks for lidar-only odometry. And so here we're kind of coupling a deep neural network with this state estimation machinery that I've been talking about. So at the front end, we take 2 LiDAR scans and we pass them through this network. And it's doing 3D point convolutions at the front end and then outputting a couple of things. So it's outputting not just some key points to pay attention to in the point cloud, but also a covariance matrix associated with each of those, as well as a descriptor. And then we actually match functions in a we match landmarks in a differentiable way. And so the output of the whole front end network is a set of matched 3D landmarks that have been matched through a descriptor. And we can actually then back propagate through this matching function, through the descriptors, and all the way back through the network to try to learn what types of landmarks to pay attention to. And so in the M step, we're holding the distribution over the robot trajectory fixed, and we're back propagating all the way back through the network to try to train the weights of it to pay attention to the right landmarks to be good at the particular task that we care about, which is lidar odometry. And I'll just show you the sort of bottom line of this. So this was just done on the Kitty data set. This is actually only a couple of days old, so you're seeing really bleeding edge stuff. And so again, we're not training with ground truth, right? And at the very beginning of this setup, we get an estimate for what the trajectory might look like, which is this blue thing, which looks very garbled. And then after a chunking away for an hour on a server, without ground truth, we're learning to do lidar odometry, which is this red thing. And so this is not state-of-the-art odometry, but it's pretty close to state-of-the-art for frame-to-frame lidar odometry. Most of the really state-of-the-art solutions are doing sliding window. So we're trying to do that next, but I don't have the results for that yet. So I think this is a little bit promising. We're sort of in one framework, figuring out how to not only train our models, but also do state estimation without any ground truth. Okay. And if we introspect a little bit into the network, we can see kind of the features that it's figuring out what to pay attention to. So in one of the earlier layers in the 3D point cloud convolutions, we can see that we're starting to pay attention to sort of either the road or vertical structures, or even the interface between the road and vertical structures. So we can see like activations on different points in these different point clouds, which, these are reasonable features to pay attention to for the odometry problem. Okay, so I think that was actually my last slide. I'll just put this video up to sort of show what we'd hope to be able to do. That's as far as we've got sort of on this generalizable problem. Eventually, what we hope to be able to do is just drive around and then output an algorithm that does something as robust as this without having to spend 2 years of engineering all of the software and testing it for so long. So not there yet, but that's sort of where we're going. So happy to take any other questions.
Wonderful. Thank you, Tim, for an awesome talk. That was really stimulating. I'm sure we're going to have lots of great questions. And I have to say, along the way, I've been putting a few on hold as we go until the end.
No problem.
I'd like now to invite Stephen Williams. Would you like to unmute yourself and ask your question?
Yeah, actually, I've got two questions. One I put in the chat, and then one that's kind of on the latter half. So when you were talking about
the chat when I'm full screen, so I'll just
no, that's fine. When you were talking about sort of the additional views when you're running, multiple tracks, have you done any work on sort of, sim to real kind of synthesizing additional tracks? Kind of thinking about, can you hallucinate what things look like under different conditions, modeling lighting changes and things like that, and use that to kind of provide additional simulated views of what the robot thinks it should look like that it could check against if it was repeating?
Yeah, so I have not done that. So this, but others in my department have done that. So John Kelly's recent PhD grad, Lee Clement, put out this paper called How to Train a Cat. And so CAT stands for Canonical Appearance Transform. And so what he actually tried to learn was he didn't do what you said, which is to hallucinate different views, but what he did was try to learn a way to make all of the views look like some canonical experience, sort of the inverse of what you just said. So that was one thing that's been tried. We haven't tried in the sort of classical multi-experience framework synthesizing different views, but we have done that when we've been trying to train networks to directly match things across a wide variety of conditions, but not to a lot of success so far, I would say. So we've tried changing in sort of cheap ways, changing the brightness of images and putting boxes on images to sort of introduce sort of like visual dropout, things like that. But I wouldn't say not enough success that we actually published anything on that yet.
I think my other question is more about, if you're doing this predict ahead work and sort of the stuff you're talking about at the end, does that feed into any kind of exploration or active learning where you're starting to say, okay, where should I go to improve my model, and find new trajectories and things like that? Are you thinking along those lines in terms of, deciding
we have not
where to
been
look?
thinking along those lines yet, but I know exactly what you're asking. I think one of the big downsides, at least for deep learning, is that we don't get a great sense of the uncertainty in the model that we've learned, and sort of where it's got a lot of training data and where it's confident in the answer and where it isn't, I would say. So, if we're using this expectation maximization framework, if we're learning parameters for the models, the parameters don't come along with uncertainties. And so it's hard to do active learning around that, but we can actually swap out those parameters for random variables with priors and then try to build distributions over models, and then it's sort of more amenable to the active learning approach that you're talking about. But I think we're so far away from that, at least in our lab right now, that we haven't been thinking about it.
So one of my students actually, we had a paper at ICRA about using Bayesian neural networks to sort of do that sort of thing, to get some notion of the uncertainty of the classifications that could then help drive
yeah, so there have been
exploration.
people looking at that, right? So like trying to do dropout at, even for neural networks, trying to do dropout at test time to try to get the model uncertainty. There's some question around like what what uncertainties is that actually going to produce. But yeah, I think it depends on the models that you're using. Some of them come along with like nice ways of getting uncertainties, and then you can, pipe that into an active learning framework, and others, I think it's less easy to do that.
Thanks. Great talk.
Thanks.
Ian, I believe you had a question lined up.
Yeah, hi Tim, thanks. Great presentation. A really nice mix of kind of empirical results and kind of basic ideas. I had a question, I guess, about the use of the EM algorithm. We've used EM a whole bunch for linear and nonlinear system identification, and it has some nice properties, but it's very, very slow to converge, especially as you approach, as you approach the maximum likelihood point generally. And so usually we apply it in contexts where you have very simple calculations for the smoothing and the updating the Q function part. If each step in the EM alternation is some kind of neural network fitting, how does that work? How are you deciding when to switch from E to M, and how you're deciding when to terminate the EM process?
Yeah, those are all good questions. I don't have definitive answers, so I should say that I guess we're doing something more like generalized EM, meaning we don't fully minimize the M step, right? So we just have to go a little bit better on each M step. And so what we've been playing around with is, if it's a neural network we're training on the M step, we do a few iterations of stochastic gradient descent to try to improve the model parameters. And then we can go back and do an E step, and then do some more stochastic gradient descent. And we played around with different alternating algorithms, I guess. I don't think there's a definitive one that works the best on every problem, though.
Yeah, and I guess a second question is that generally EM will learn, or if it works, will learn a valid state space for prediction of the system, and it may converge to, there's no guarantees what kind of state representation it will converge to, but are you finding that it kind of learns interesting or useful state representations, or is it just kind of a huge pile of states that you can't really interpret?
Not sure I totally understand what you're asking there. So
I guess it's another way to put it is it's kind of the representation learning question. So in the context of linear systems, what you will learn is a state space which is an arbitrary non-singular transformation.
Sure, the state space representation for a given transfer function is not unique, right?
Exactly. And for nonlinear systems, it's also not unique, but under kind of arbitrary invertible nonlinear transformations.
Yep.
So I guess you could learn all sorts of different possible representations of the state, and some of them might be more compact or sparse or useful in different ways. So I wonder if you've looked at the kind of state representations that come out of this process, because that's kind of the idea between deep learning.
I got two answers to your question. So the first answer is we can force it to come up with a useful underlying state representation if we give it not perfect, like we don't assume we know ground truth, but if we had some like noisy training data for the ground truth, right? So maybe you have GPS that gives you noisy positions, right? So that's going to sort of constrain it to output something that matches that reference frame. So a lot of the problems with these is sort of like, what reference frame does the state come out in? That's sort of one problem. And so you can encourage it to come up with a particular state representation by giving it some noisy ground truth, I would say, is one thing. And that's been effective for a couple of problems. Often if the measurements are complete enough, in other words, they're sort of measuring the state more directly, rather than like you've got position, velocity, acceleration, and you're only measuring position, that gets a bit trickier. But if it's like in the car example, that one worked well because the measurements were actually measurements of pose against a 3D lidar map, but they were noisy, right? And so the observation model is actually pretty simple to learn there. But you're right. It's not a panacea. Just because I'm saying EM, it doesn't mean it's going to sort of automatically solve the representation problem. But the other half of my answer would be that I think in robotics, we've spent a lot of time trying to make sure we're really good at state estimation. I'm guilty of it even more so than most because I wrote a whole book about it. And at the end of the day, like, do we actually care? As long as we learn a state that's good enough to let us solve the problems that we care about, to make the robot move around, maybe that's good enough. And so I've kind of tried to force myself to give up on caring what the state estimate is and try to focus more on, when we go back to the graphical model, just problems that where performance can be measured on things that I can directly get from the robot, right? So like if I can measure the performance directly by comparing the camera images that I get to some desired camera images, that's good enough to say whether I'm tracking a path. I don't need to know where the robot thinks it is in the world.
Mm-hmm.
So I guess I've just tried to get away from caring what the latent trajectory is. As long as it's a good predictive model for the problems I care about, then maybe that's good enough.
Great, thanks.
So I see that we're a few minutes past the hour and some folks have had to go, but if it's all right, Tim, we'll keep you on for a few more minutes if there are a few more questions from the audience, if that's all right. And so if you do have a question for Tim, please do raise your hand or type it into the chat box. And I have one that's sort of a follow-up to that last statement. Maybe I can ask you to elaborate. So this idea that, we don't care so much what the exact state is so long as it's a useful estimate. And going back to the first part of the talk, you presented this teach and repeat system that, it gives up on a lot of things. It's topological and not global. There's no loop closure. It's sparse and not dense. And that's sort of in contradiction to a lot of the work that's going on now, which seems to want to build a huge metric map of everything that's consistent across the whole planet. Can you talk about some of the pros and cons and when you would want to use one or the other?
So now you're talking about like teach and repeat particularly, not what I got here on the slide.
More not what you're on the slide, more the philosophy of, it doesn't have to be exact so long as it's useful.
Yeah, so I guess I'll just put this slide up as I talk. So I guess at the end of the day, we spent in robotics 10 years trying to make really pretty pictures of what the world looks like. I was one of those people. But it's not obvious to me that it's necessary in order to solve some problems in robotics. And so I think teach and repeat in a way it's almost deliberately flying in the face of all the work that we did on SLAM and all those things, right? It's sort of showing that you can get away with far, far less and still possibly even do better at something like tracking a path by throwing away the need to build things in a global reference frame. And so I guess my philosophical retrospective on this is that question everything, right? Just because a bunch of people are working on something in the field doesn't mean that that's the right way to make your robot solve your problem. So do I need a really perfect picture of the world in order to drive around? I don't think so. I think VT&R shows at least one example where you don't need that. Maybe Elon Musk is right. Everyone working on self-driving is building these like super dense HD lidar maps of cities in order to drive around. And Musk is saying, well, no map. Often in the media, he's quoted as saying no lidar, but really what he's saying is no map, right? Approach every intersection as a new experience and work it out for yourself and decide what to do.
Right.
Maybe he's right, but I guess my philosophical bent would be question everything and decide what's the best thing for your robot problem.
Seems like really good advice. I just noticed in the chat, Shalto has shared a link with everyone, more of a comment than a question. It's a note on moving away from exact state estimation and towards a focus on downstream tasks by Mudzero, with a link to a paper there. Instead of learning models, which are good at predicting the next state. Okay, so thanks for that comment, Shalto. Some more questions from the audience. I do have one more, Tim, for you, and it's a little specific, so maybe I should have asked it earlier, but In the later part of the talk, you're talking about learning this in this graphical framework, which is very robotics friendly, right? So this fits really well into the way that we think about doing things in robotics. In parallel to that work at the computer vision conferences, we've seen people learning odometry and depth in an unsupervised way in what I would call more of a camera-centric framework, right? So they're thinking about warping what the camera sees in one frame to match what it sees in the next frame, right? So everything's camera-centric. The frameworks seem very different to me, and I wonder if you've thought about pros and cons of each and whether they would fit together or if one supplants the other in robotics.
Yeah, that's a great question. There's lots of examples of that. These sort of like predictive state representation techniques that sort of don't bother with the underlying latent trajectory, I think are interesting. I guess, both are valid. We've been exploring this one because I think it becomes possibly more introspectable at the end of the day. Maybe I'm still clinging to states too long. Maybe I should just give up on them altogether. I don't know, but this is the thing that we're trying first. I think it maybe is a more gentle transition from what we're used to in robotics to at least trying to give up on having ground truth, but still having a latent trajectory. I think I'm okay with that for now, but yeah, that giving up on the state altogether might be the right way to go. I'm not against that.
Interesting times. I see that, thanks for that. I see Eduardo has a question. Please, Eduardo.
Yes,
Hey, Eduardo.
hello, how are you, Tim? Excellent presentation, really enjoyed. And since you start touching the application of deep learning to standard algorithms that we did just using basically deterministic or statistical method, I would like to know what you think about this. There is a significant transition to not to forget, but to start to reformulating the many algorithms with deep learning. For example, you can see even trivial things like bird-eye view. I mean that they have enormous limitation. I mean, or what appear to be physical limitation of the resolution of the camera that it actually is pushing us in order to go into basically complete different solution, learning like with guns and everything. You see like Tesla, how they're learning everything, and even they are forgetting about the basic algorithms of line detection, everything. They are learning this. It looks like we need to seriously think about that. I mean, that, and also, as Stefan and you have a discussion, I mean, that this method appear to work very well, but we don't know when they fail. Okay, and you can imagine that there will be trivial cases in which we can have a catastrophic fault. So, what is your thinking about all of this? Is this the way to go, and then start thinking about how can we guarantee robustness? I mean that, or we go in the middle. So your impression, Tim, please.
Yeah, lots of great thoughts and questions in there. So I guess we should explore everything. So it's great that people are exploring. Some people are still doing fully classical solutions. Some people are doing, deep learning end to end. I guess I'm sitting somewhere in between these two things because I like math, and I don't want to give up on math, and I don't know how to supervise students when they don't have equations for me to look at. So out of survival mode, I guess I still want some math in my students' work. But I think the answer for me sits somewhere in between. Like usually when these big trends come in a field, the pendulum swings one way, the pendulum swings the other way, and then 10 years later, we figure out that it should sit halfway in between. And so I'm skipping the other part and going straight to the halfway in between. And so something like something like this, which I didn't get into a lot of detail, not this one, sorry, this one kind of makes sense to me. So like we're still using these nice state estimation tools under the hood. And in there, we can still incorporate things like outlier rejection, M estimation. You could incorporate any of like Luca Carlone's excellent work on teaser plus and things like that. The certifiable algorithms at the back end level. But then we can still get the benefit of the representational power of deep learning at the front end, where we're able to sort of, I mean, the hope in looking at this for me is that deep learning will allow me to learn something like features that would be appropriate to my particular data, right? And so hopefully we can start to learn something more like semantic level features rather than these low level point features that we engineered by hand. And that's sort of the promise of deep learning. But to me, it doesn't make sense for deep learning. In robotics, we need to be very data efficient, right? And so we can't afford to, especially in academia, we can't afford to like get 17 petabytes of data in order to train an end-to-end autonomy solution on a giant server. And so for me, there's also this practical reason of like, I just don't want training to take a long time. And so the things that I already know about, like 3D geometry and robot poses and outlier rejection, I don't want to give up on those because I don't want to waste training data and compute to figure that stuff out since I already know about it. But maybe I can figure out the 3D landmarks that I want to pay attention to, for example. So I think the answer is probably going to sit somewhere in between. And then we can get these guarantees at the back end level. And I very much like Luca Carlone's stuff. I think moving towards these certifiable backends is a very cool idea. But what that then allows you to do is make a lot of mistakes on the front end, right? So the deep learning can make lots of mistakes, and then the back end can kind of make guarantees that they can handle it.
Okay, well, thank you, Tim.
That's good. Thanks for that, Tim. I think we have time maybe for one more question, if that's all right, and then we'll call it. I see it's more than quarter past the hour now, so thanks for being so generous with your time, Tim. Tristan Fritz, I see you've got a bit of a technical question, so I might ask you to unmute your microphone and ask that directly, if that's all right.
Yep, no worries. So yeah, I've done a little bit of work in trying to do like latent dimensionality reduction and trying to do like planning in this kind of like latent space. But I found that it's really difficult to interpret when you kind of encode state space to these arbitrary latent dimensions. Is there a nice way to learn disentangled representations and kind of align those like principal components that you've learned with something that's like useful or that you can map back to reality so you can kind of actually have some kind of guarantees or interpret the model?
Yeah, I think this is related to the earlier question around state representations and how do you know what you've learned? I guess the answer that I gave to the previous question would be my go-to answer for this one too. So like in this example, if I was trying to make sure that I had an interpretable latent trajectory representation that I learned, if I had some weak labels for the state that I could also put on here as factors during training. So if I had some, not perfect ground truth, but just some kind of ground truth that's got some even unknown noise associated with it, even maybe some outliers in it, I could still attach those as factors in this model. And it would sort of ensure that the state representation that I learned would be compatible with whatever, for example, reference frame that ground truth was provided in. And then I could be sure that I've tried to learn something that I know what frame at least it's in.
Gotcha.
So we've done some stuff like that.
It's trying to do like weak supervision, that kind of stuff, rather than like fully unsupervised.
Yeah, which I think is fine, right, in robotics. I mean, the less ground truth we require, I think the more flexible our methods, but if we need some weak supervision in order to make the problem easy to solve, I don't see that that's an issue in robotics.
Yeah, makes sense. Thanks.
And it's compatible with this framework, by the way.
The part of what you're doing too is hand coding how the latent space is being interpreted, and that puts a lot of constraints on what gets learned. And that's the crux of that computer vision community approach to this. They interpret their outputs as trajectories and depth maps, and so that you have a highly structured learning framework means you're going to be learning, I think, more interpretable representations. Yeah. Okay, so thank you, Tim, for a great talk and for being so generous with your time. Everybody, please join me in thanking our speaker, You can type thanks into the chat window or clap into your microphone if you please. Thank you so much, Tim, for being with us today. And I hope we do have a chance to have you down to visit us when that's possible. It's a bit of a shame you've never been to the ACFR, but hopefully we can fix that in the near future. So
sounds great. Thanks so much for listening. Hope to see you all at a conference sometime.
Indeed.
All right, take care.
All right, we'll see everybody at the usual time next week. Bye now.